So, Finger Lines Math and History, and we are going to be trying to defy gravity. So this video is literally called Defying Gravity. So, in the last physics videos, we've been taking a look at the whole idea of speed, velocity, acceleration, displacement, all that stuff. But we're going to get into a new unit called Defying Gravity. So, when we talk about the physics in this class, we're literally talking about the physics on Earth. And in the last video, we've been taking a look at the so-called the forces on the Earth. Like we've been talking about the forces of gravity on Earth. We've also been talking about the mass on Earth. And we've been also talking about the workload that Earth gives us. We also realized that the acceleration for gravity is 9.8 meters per second squared. And not only that, yeah, that's pretty much what we have for Earth. But many scientists, mathematicians, and those who study physics realize that Earth isn't the only thing in the so-called universe. And where there's universes, there's galaxies. And the crazy thing is, it gets a lot bigger. Gravity can actually be different anywhere in the universe. You can weigh heavier or lighter on like the moon, Jupiter, Neptune. Well, even if Neptune and Jupiter actually have land, then yeah, I wouldn't think that's a good idea. So, with universal law, that is basically saying, hey, it's the same idea, but with different formulas. Because the formulas we made are on Earth, because we live on Earth. But what about universal law? We like to study and understand gravity by using this formula. F of g equals the gravity, the mass of one planet, multiplied by the mass of another planet or an object, divide that by the distance squared, or we could say the radius squared. That is a formula that we'll be using. The universal law for gravity is g is always going to be inserted into that thing equals 6.67 times 10 to the negative 11th power meters cubed kilograms per second squared. Very similar to the whole idea of 9 meters per second squared. So d and r is the distance from the two bodies. But not only the distance in the two bodies, we're also talking about the radius of the two bodies too. If this was the Earth and this was the moon, and the moon goes into orbit, well, it kind of already has, not only there's gravity and inertia keeping our moon in a stable orbit, but what we're talking about is when we use that formula up here, we're talking about the center of the Earth and going to the circumference of it. Then we go from the distance from the Earth to the moon's circumference. Then after that, put that into the radius of the moon. So not only we're talking about universal law, we're also talking about the radius of the Earth and the distance between the two bodies, like the Earth and the moon. Picture it like you're trying to swing a yo-yo around in circles because you're bored. What we're going to do is we're going to be using this formula to understand what is the gravity on Earth. What we're not going to do is try to find the gravitational pull between two objects. Because there's an actual little, not a proof, but an amazing idea of why we get our answer. And there's an actual Easter egg behind it. So to find the gravitational pull on Earth in terms of like newtons, you need to find, using the gravitational or universal law, multiply it by two masses, divided by your distance squared. What we're going to do is not use the two masses. We're just going to use the mass of our planet Earth and use the radius of our planet instead of the distance. So here's what the stats are. Find the gravitational pull on Earth. So the mass of the Earth is 5.98 times 10 to the 24th kilograms. The radius of the Earth is 6.38 times 10 to the 6th meters. So that is from the center of the Earth, the core, to the crust outside, which is grass. And tell me in 40 seconds when you touch grass, if you ever do. We gotta use the formula G equals universal law of gravity number times the mass of the Earth divided by the radius of the Earth squared. And what's different is we're trying to find the gravitational pull on Earth, not the gravitational pull on two objects. So that's why we don't have an M1 and M2, because that's literally the mass of the planet, not two objects. So let's get started. Hang on. What if I told you that instead of using a calculator, you can actually do this by hand? So let's see what happens. We write the formula G equals 6.67 times 10 to the negative 11th power. That is going to be our gigantic letter G. Then we have to multiply that by 5.98 times 10 to the 24th kilograms. Mass of the Earth. Divide that by the radius squared. That is 6.38 times 10 to the power of 6. But how are we going to solve this problem manually? Well, what we can do is, since we have exponents of this, that, and that, we can use exponents to help us figure out why and what we can do without a calculator. We have to mess with the bottom one because that's the radius squared. Exponents always come first in order of operations. So we have 6.38 times 10 to the power of 6 squared. What we can do is split it up. 6.38 squared and 10 to the power of 6 squared. 10 to the power of 6 squared is going to be a lot easier because you don't have to expand it out. And not only that, it also follows the rules of exponents, which you probably learned in Algebra 1 or Algebra 2. So, the rule when you multiply an exponent by another exponent, in terms of that, our model number is going to be x, and our exponent is going to be a. When we have parentheses and want to multiply that, we're going to say our other exponent is b. So that can simplify to our model number being x is simplified to ab. So what you do is multiply the exponents. So 2 times 6 is going to be 10 to the 12th power. And yes, you're going to have to do that with a calculator, which I kind of lied with. But if you do that with a calculator, you get 40.7. So here's what happens to our new equation. G equals 6.67 times 10 to negative 11 times 5.98 times 10 to 24th. Divide that by 40.7 times 10 to the power of 12. So now we gotta mess with division. We can divide 5.98 and 40.7 manually, but what we're gonna do is leave it. Here's what we're also gonna do. We're gonna kind of do things in a more liberal way. You see how we have exponents and constants? Well, what we see is there's an exponent right here, there's an exponent right there, and there's an exponent right there. All the rest, here, here, and here, are all constants. So let's start with these because we multiply. So when we have 10 to the negative 11th and 10 to the 24th power, we're going to get 10 to the 13th power because we add the two when we multiply. But that only leaves us with one thing. 6.67 times 5.98, divide that by 40.7, okay? 10 to the 13th power, subtract that by 12, because that's 10 to the 12th power, we just get 1. 10 to the 1st power. So see what we're doing? We're putting the exponents on the right side, and the constants on the left side, because we're trying to mess with this, this, and this, the lines, at once, and then mess with the exponents at once. So if you do 6.67 times 5.98 divided by 40.7 to 10 to the power of 1, you will be surprised that your final answer is going to be very, very shocking. Your final answer is your G, your gravity on Earth, is 9.8 newtons. 9.8 newtons meters per second. No. I was confusing that with the acceleration of Earth. But the gravitational pull on Earth is 9.8 newtons for every 10 kilograms. So that is why we have 10 to the 1 power, because that's 10. And that explains the video. I hope this video has helped you understand defying gravity. Thank you for watching Cal Penguin Life's Math Industry. Like and subscribe.